Welcome again in the new session. In this session, we have to discuss one theorem to homomorphism, and then we move to the isomorphism. In the last class, we have to discuss some results on the homomorphisms, and the last result we have to prove this is a kernel of a phi is equal to identity, then the phi is 1 1. This is vice versa if and only if condition is hold. So, now I just today start with this theorem. This theorem is let phi from G to G1 be G and G1 be any two groups of the binary operation star and star O be a homomorphism. I just take this G as a binary operation with this, and then we have a G1, we have a some O like this. So, these two groups and phi from G to G1 be a homomorphism. Then we can say that if G is cyclic, then G1 is also cyclic, and G is abelian, then G1 is also abelian. So, we just proving this. If we have a from G to G, if this group G is a cyclic, then we have to say that this G1 is also cyclic, and if G is abelian, then G1 is also abelian. So, let us start with the first condition. If G is cyclic, then G1 is also cyclic. So, first assuming that G1 given G is a cyclic, if G is a cyclic, that means this can be generated by some elements of a G, and then suppose we have to assuming that G is generated by A. So, this means G is generated by A, that means all the elements of a G can be some powers of a this A. And now we have to show that this G1, you know, this phi from this G to G1 is a homomorphism, and that means this is elements of a, if elements of a this is equal to G, then this is mapped to this is equal to phi, this element is mapped to some phi of G types element. So, that means if we have to choose any y1 is the element of a G1, then there exists some x is the element of a G such that phi of x is equal to y as phi is onto. So, we just take phi is because we have given in the statement is this is from G to G onto G group G dash. So, this means this is we have a clearly if you see this we have a given phi from G to G1 is homomorphism and also onto. So, by onto-ness, if we have any element of y is the element of this G, then this G1, then there exists some element x is the element of a G, then we have such that this is phi of x must be equal to y by the onto-ness of this. And now, this x is the element of a G, and this means G is generated by this means x can be written as some powers of A. So, we can say that x is written as a to the power m for some integer m. So, if this is equal to this, now because y is equal to you have a y is equal to phi of x, phi of am, and then phi of am is nothing but is equal to can be written as a phi of a up to a, that is equal to you have a m times, and now because phi is giving you a homomorphism. So, this can be written as a form of a phi of a is equal to phi of a, then again you have a this is equal to m times, and then this can be written as a phi of a to the power m. That means y is the element of a some G1, and this y can be written as a some phi of a to the power m. Then we can say that this is clearly we can write into this form. So, this is equal to this. So, y is the element of this G1, and y can be written as a sum of phi of a to the power m. That means y can be written as a phi of a is nothing but this is the element of a G1, and then every element of this G1 can be written as a some powers of m, and if written as some powers of m, that means this is a cyclic. So, this means clearly we can say that if G1 So phi can be generated by this G1 can be generated by this phi of A, and then hence G1 is a also is a cyclic. So we can prove easily, that means if we have any which element by the ontoness is this, we have to using the ontoness as phi is onto, then we have proved that clearly G can be G1 can be generated by the phi of A. This means every element of a G can be written as a some powers of a phi of A, and that means we can say that, and this is G1 is a clearly is a cyclic. So the first one is proof is completed, and then now we to move to the next one. We have a, if again G is a abelian, then we can say that G1 is also abelian. So if G1 is abelian, they can means we have to again we take some two elements, A1 and B1 is the element of a this G1, and phi is on to. So this means if A1 and B1 is the element of a G, then there exists some elements A and B such that you have to say that phi of A is equal to, we have to A1, phi of B is equal to, we have a B1, and now we have another condition, we have given G is abelian. So we have given AB is equal to B of A. Now we have to show that A1 B1 is equal to, you have a phi of A, phi of B, and the phi is homomorphism, then we can write as a phi of B. Again by, because G is giving you a abelian, so these A and B are the element of a G, that means AB is equal to same as a B of A. By the condition AB is abelianness, so this can be written as a phi of B of A, again using the property of a homomorphism, and then we can say that this is equal to phi of B, phi of A, and now phi of B is nothing but is equal to, you have a B1, and then phi of A you have a A1. So we have to show that if A and A1 B1 are the any element into the G1, and then we show that A1 B1 is the same as a B1 A1. So there is a, if phi is a onto homomorphism, and then we can simply say that if G is a cyclic, then G1 is a cyclic, and if G is abelian, then G1 is also an abelian. So this complete the this proof of this theorem. So by using this we have to clearly say that. So this means we can simply say that using the here using the we have to using here the homomorphism, and this means we have used the abelianness of commutative condition for G, and then again use the homomorphism, and then we have to show that this means this G, if G is an abelian, so then we can say simply say that G1 is also an abelian group. Okay, now we move to the next article, and that article is a isomorphism. So you know that before this we have to isomorphism, we have simply, if you we have a G and this G is a binary operation, and this is to map is a we have a G1 with the this binary operation, and there is a phi from G1 G to G1, and if this phi is first is homomorphism, and you have a 1 1 and also on 2. So if this is simply, we can say that a homomorphism phi from G to G, a homomorphism from which is also is a bijective, then its called is a isomorphism. Isomorphism, before giving the definition of isomorphism, means simply isomorphism means we have a these two groups are looks is different, but they have exactly the property of this look like the same, but there is a different. For example, I just start this before definition, I just construct a Cayley tables of two groups. So one is a Z3 under addition, and one is a S3 is generated by 1 2 3. So this is a G3, and this is a element of a, if we have to take a this group is simply is a element of identity 1 2 3 and 1 3 2, and this is clearly is a subgroup of a S3. So, I take these two groups, this is a group and this is also is a group, then you can simply say that if we have a construct a table of these two groups. Now, you see under addition modulo 3, this is 0 1 2 0 1 2, and then you have to identity element here, and then this is clearly group, and here as identity element we have a, and then clearly. Now, you see the 1 is in itself inverse, and sorry, 0 is itself inverse, 1 is inverse of a 2 and 2 is inverse of a 1. And similarly, you can see this is identity, and this is clearly is a this, and this is this. Now, you see clearly, we know that by the property of homomorphism, this means if we have to define a map from this Z3, say this generated by this 1 2 3, and then you can see if it is homomorphism, and if it is homomorphism, then we can say simply say that that means we can say that identity of E is the same as a E1. And then also we have to, if we have a phi of x inverse is the same as a phi of x ka whole inverse, means preserving the identity element, preserving the inverse also for the mapping. If you see this, from this we have to define as, if suppose this is a phi of 0 is mapped to identity, this is sorry, phi of E, phi of 0 is nothing but is equal to, you have identity, and now phi of 1 is nothing but is equal to, I just said that the inverse of a 1 is equal to 2, and then this is 1 2 3, inverse of a, this is phi of 1 1 3 2, and then we have phi 2 is equal to 1 2 3. And now if you see this, if we define in such a way, then clearly this is a 1 1 and onto mapping, because this we just say that identity element this, and 1 can replace into this and 2 can replace this by the setting of the correspondence. We just say that 0 because 1 is equal to 1 2 3 and 2 is equal to 3 2 1. If you see there is a table, in this table if we have to replacing this like this way, for example, I just show you 0 1 2 0 1 2 0 1 2 1 2, and then 2, and then you have a 0, and then you have a, this is a addition modulo 3, and 2 plus 1 0, and 2 plus 1 4 is equal to 1. I just say that in place of a 0 I have to writing is a E, and then in place of a 1 I just write as a 1 2 3, and then in place of a 2 I just write as a 1 3 2. And now here is also we have E 1 2 3 and 1 3 2. Here as also is a 0, 0 is nothing but is equal to E, 1 is equal to, you have a 1 2 3, and then is equal to 1 3 2. Here is also 1 2 3 and 1 3 2, you have a like this form. And again this is a 2, 2 means 2 is equal to, you have write as a 1 3 2, and then 0 is equal to identity, and 2 is equal to, this 0 is equal to, you have identity, and 1 is equal to, you have a 1 2 3. Now, you see if these two tables, they are look like say identical. If we have a in place of a here in place of this identity we write a 0, in place of this 1 and this we getting this table, and if writing in this form is equal to, we have to getting this table. So, that means corresponding of this clearly they are 1 to 1 corresponding is there. So, we can say simply if we have to just show you this thing. So, we see that two tables differ only in the names in the symbols and not their positions. If we name the mentioned correspondence letter phi by writing phi 0 is equal to identity, phi 1 is equal to 1 3, phi 2 is equal to 1 3 2, and then the constructed diagram of this mapping we see is phi is bijective mapping with the property of this phi of A plus B is equal to phi of A into phi of B. You can clearly say that phi of A plus B means we have to take a phi of 0 under modulo 3 1 is equal to phi of 1, and phi of 1 is nothing but is equal to, you have a 1 2 3, and this is equal to 1 2 3. And now if you take a phi of A, phi of 0, phi of 0 is equal to, you have a identity, phi of take a multiplication of this phi of B is equal to, you have a 1 3 2, and then this is nothing but is equal to, this is the same as a 1 2 3. So, this is equal to satisfy this condition. Similarly, for other also, if you take a 1 and 2, and then we can verify this is equal to phi of 1 composition multiplication 2 is equal to, you have a phi of 0, and then phi of 0 is equal to identity. Now we have to go to the reversely. If we have to take a phi of 1 is equal to, you have a 1, 2, 3, and then you have a phi of 2, and then you have a 1, 3, 2, and if you take a multiplication of these two, clearly you can say that this is equal to, you have 1 goes to 3, and then 1 goes to 3, 3 goes to 2, and 2 goes to 1, and 1, 1 goes to 1. So this means 1 goes to 3, 2 goes to 1, 1 goes to, you have a 3, and then 3 goes to 2, and 2 goes to 1. That again we have to just, so we have to just say that clearly is nothing but is equal to, we have to getting the identity element. So this is clearly, you just, if you write this composition of this, we have to write phi 2, sorry, phi 1 and phi 2. If you write the composition of these, you have a clearly 1 goes to 3, and 3 goes to 1, so 1 goes to 1, and then you have a 2, 2 goes to 1, and 1 goes to 2, so this way 2 goes to 2, and then 3 goes to 2, and 2 goes to 3, and 3 goes to 3, so that means is equal to, if you take this product of these two, clearly you have a identity. So this means we can say that this satisfies this condition, this map. So I just say that into this form, 0 to this, 1 to this, and then clearly you see this by this figure, you easily say that this is a bijective, because it's 1 to 1 corresponding, and also every element has an inverse image is also there. So this means clearly this set is a bijective. So this means we can say that this is bijective, and also this preserving this phi of A addition modulo 3b is the same as a phi of A composition phi of B. We have any element, I just already showed that 0 plus modulo 3. If you take for example, if you take a modulo 3 2, then is nothing but is equal to, you have a phi of 2, and phi of 2 is equal to 1, 3, 2. And if we have to calculating the phi of 0 into phi of 3, phi of 0 is equal to identity, sorry, phi of 2, and pi of 2 is equal to, you have a 1, 3, 2, and then is nothing but is the property is equal to 1, 3, 2. So this means this again said 3. This means this condition is hold, and 1, 1 and on-to-ness is there. So that means we can simply say that we have a two groups is this, look likes is different, but they are exactly is the same thing. So this means 1, 1 and on-to correspondence and homomorphism are there. So we can say that this means in this case, if we have two different groups, but they are look likes different, but if we replacing these properties, they have to say look is the same. So in this case, we can say that these two groups are isomorphic to each other. Now we have to define is a proper definition of this isomorphism. So let this by this example previously we lead the following definition is saying that two groups G and G1 are said to be isomorphic, denoted by this symbol. G1 is isomorphic to G1 if there exists a bijective homomorphism, that is phi of G is equal to G1. Yani we have a, if we are operating phi of G and then that is giving the exactly the G1, then we have to say that this clearly means we have to say that these two groups are isomorphic to each other. Such a homomorphism phi is called is a isomorphism or isomorphic mapping. So isomorphic mapping of G star onto G1. If such a homomorphism phi is exists, which is also is a bijective, then we can say that is a isomorphism, and the phi is called is isomorphism, and then we can say that these two groups are isomorphic to each other, and then we have to start with the one example. And if in place of this two different groups, if we take the same group are the same, if we have a G star is the same as a G1, then binary operation is also the same. So then this phi is called an automorphism on G. So if we have in place of a two different group, if we have to define a phi from G to G is homomorphism, is a bijective homomorphism, then this phi is called is an automorphism. So, in place of a two different group, if we have a same group is exists, then we can say that this phi is a automorphism. Okay, so now before this I just touched from the very simple example. We define a phi from z to z is equal to this clearly, and now you know that this clearly is a homomorphism. We have to prove that very simple, because these two are the groups under binary operation addition. Z is also under addition, and this 2z is also under addition is a group, and then phi of n is equal to 2n. If you want, you take a m and n are the element of a z, you can write as a m plus n, and then by the definition this can be written as a 2 times of a m plus n, and this can be written as a, because all are the integers, so this is 2 plus m plus 2n, and this can be written as a phi of m plus phi of n. So, phi is homomorphism. Also on 2 there means we have to find any element 2 and there exists some another element 2 times of this. So, this is clearly is not a problem for on 2, and 1 is trivially, if we have to take a phi of n is equal to phi of m, then we can say that this is 2m is equal to 2m, and then if 2m is equal to n, then we can simply say that m is equal to n. So, phi is a homomorphism and both 1 and on 2. So, we can say that this means this z and z to this z and this isomorphic to 2 of z. In general, we can say that this z can be we define if we take this in place of this phi map from z to mz. M is any integer I just take in this form. We have to define is a phi of x is equal to, for example, we have to define phi of x in the sense of a like this, phi of x is equal to m times of x for all x is the element of a z. So, this is clearly again is a by this in place of a 2z, we can generalize this for in the case of a mz. So, we can simply say that this z is isomorphic to mz. So, you have m is any integer we have values there. So, this means this is the one of the example we can say that this is clearly is these two groups, so z and 2z are isomorphic to each other. Now, I just take a consider two groups Z4 and the table I just by the table, if you want you can just take a we have to write in the form of a this we have to suppose we have a under addition modulo 4, then we have element is 0, 1, 2 and 3, and this is 0, 1, 2, 3 and 0, 1, 2, 3. Now, we have a is the element of a 1, 2, 3, then you have a 2, 3, 0, then you have a 3, 0, 1, then you have a 0, 1, 2 are there. And now, similarly, if we take a draw a matrix for under multiplication for 1 minus 1 I and minus I, 1 minus 1 I minus I, and this is equal to 1 minus 1 I minus I, minus 1 I minus I, then you have a 1, then is equal to minus I, then you have a I, then you have a minus I, then you have a I square is equal to minus 1, then is equal to 1, and then you have a I, and then you have a minus 1, and then sorry, this is equal to 1, and then you have a 1 and you have a minus 1. These are the two groups. So, Z4 and Z4 are absolutely equal. We need to construct a bijective homomorphism from Z. So, you know that by the property of a homomorphism, we simply say that this is identity is mapped to clearly identity. So, this means this is phi of 0 is always is equal to 1. So, this means clearly one thing is very clear, we have a this is phi of 0 is that means this is the this is 0 is always is mapped to 1. Now, we have another possibility is there, this we have to suppose phi of 1 is mapped to minus 1 I and minus I 2 is mapped to -1, I and I. There is a possibility of this is mapped to -1 and this is mapped to I and so on like this. So, we have to try to construct an bijective homomorphism from phi from Z4 onto G. Okay, just start because we know that homomorphism, this means phi must satisfy this condition. I just already, because 0 is the identity element of a Z4 and 1 is the identity element of this G. So, this means this is a property say that phi, if G is phi is a homomorphism from G to G dash, then phi of E is nothing but is equal to E1. So, phi of E and phi of 0 is always is equal to the identity of a that set is equal to G clearly. So, phi of E is means we have a phi of 0 clearly mentioned is equal to 1. And now, so we have to just next thing we have to just say that suppose we have to now we have a 1. Suppose we have to define y phi 1 is equal to -1. Now, the image of an inverse element must be equal to the inverse of the image. And now you see 0 is the inverse of a 0 and you can see that it is equal to, we have a 0, 1, 2, you see this clearly, 0 is the inverse of a 0, 1 is the inverse of a 3, then 2 is the inverse of itself and then 3 is inverse of a 1. So, now by the this property inverse of, if this is equal to this, then phi of 3 is also the inverse of a -1. Now, you can see inverse of a -1 is equal to -1. So, this should be phi of 3 should be also equal to -1. Because we have a inverse is also the preserving the inverse of also. So, that means in this condition we satisfy the phi is bijective, or it will establish that is isomorphic, thereby proving the absolutely equal. We would have to phi 3 must be equal to -1. So, phi 3 is equal to, you have to just taking phi of 1 ka inverse, phi inverse 1 ka inverse is equal to is 1. So, 1 ka whole ka inverse, phi of 1 whole is equal to, we have to taking is equal to -1 and -1 ka inverse kya hota hai is equal to itself. And now, we have to show that phi of 3 is also -1 and phi of 1 is equal to -1. That means what? We have to just say that phi of phi 3 and phi 1 are the same, but 3 is not equal to 1. So, this means contradicting the your 1 condition. So, that means if we choosing phi 1 is equal to -1, then we can say that phi 3 is also -1. So, in this case we can say that phi 3 and phi 1 is phi 3 and phi 1 are the same. If phi 1 and phi 3 are the same, but we need a bijective, that this is not a bijective because 3 and 1 are different elements into the group Z. So, these 1 and 3 are the two different elements, but their images are the same, that means this is not a 1 1. So, this means this cannot be defined from phi 1 cannot be equal to phi of is equal to -1. So, that means now we have to choose a different, so a more appropriate choice in the sense that is avoid the above difficulty state phi of 1 is equal to I. And if the condition of this inverse, now you see if phi 1 is equal to, we take a I, then you have a phi 1 phi of 3 is equal to, you just taking is a this is equal to, you have to taking I in place of this, I just write because phi of 3 we take into this form, phi of 3 is equal to, we write in the form of a phi of 1 ka inverse, and this can be written as a phi of 1 ka whole ka inverse, and then phi of 1 is equal to, you have a I ka I inverse, and I inverse you have to just see that this is nothing but is equal to you have a -I, and in this case you can see this phi of 1 is equal to I, phi of 3 is equal to -I, and then we have to just further require the modular property. Phi of 2 can be written as a phi of 1 plus 1. So, phi of 1 into phi of 1, and phi of 1 is equal to I into I is equal to -I. So, we can define phi of 0, we already know that is equal to 1, and then we have to showing that phi of 1 is equal to I, and then by using the inverse property 3 inverse of a 3 is the same, phi of 3 is the same as a inverse of a 3, then phi of 1 inverse, and then 3 is the same as a 1 inverse, then whole inverse, then this is phi of 1, we have to choose I, the inverse of I. Now see, inverse of I is equal to, you have a, by this clearly you see here inverse of a I is equal to, you have a this is clearly you have a this thing. So inverse of I is equal to, you have a minus I. So we say that is equal to minus I. So this means we say that phi of 3 we have to define in the form of a minus I, and then phi of 2 we can, using the homomorphism condition, we defined in the form of a phi of 2 can be written as a 1 plus addition modulo 2. Then by the homomorphism, this is a phi 1 into phi 1, and phi 1 we have to take as a I, then I into I is equal to minus 1, and now you see into this form. So in this case we can simply say that if we have a two groups, this we have a into this form we have a two groups. This is so we take a 0, 1, 2, 3, and then we have a another group of order 4 is equal to 1, then you have a minus 1, you have a I, and you have a minus I. Then 1 is mapped to clearly is equal to 1, and now you have a sorry, 0 mapped to 1, and 1 is mapped to, you have a clearly is equal to I, and then 3 is mapped to, you have a minus I, and then 2 is mapped to, you have a clearly is equal to minus 1. Now by this figure you can see easily that all the elements of this as a clearly is a bijective and also satisfy the condition of a homomorphism. If you take this if you want to take a homomorphism of any two composition of this phi of, if you want to take a phi of 0 plus modulo 4 1 is equal to phi of 0, phi of 0 is equal to 1, and then phi of 0 plus into phi of 1, phi of 0 is equal to, you have a 1 into phi of 1 phi of 1 is equal to, you have a I, and then you have a into I is equal to I. So this is satisfy. If you want to take a 3 and 2, suppose we have a phi of a 2 addition modulo 4 and 2 3, then is equal to phi of 3 3 plus 2 is equal to 5, and 5 is equal to phi of 1, and phi of 1 is again you have a, you define as a form of a I, and now we have to check in the form of a phi of a 2 into phi of 3, phi of 2 is equal to, you have a minus 1, and then phi of 3 is equal to minus I is again I. So this is also satisfied in this condition, and then you if you want to take a phi of 1 plus modulo 4 3, then you can say that phi of 1 this is 3 plus 1 is equal to 4 phi of 0, and that is equal to 1. And now we have to take a phi of 1 into phi of 3, phi of 1 is equal to, you have a I, and phi of 3 is equal to, you have a minus I, then you have again 1. So this means all the homomorphism conditions and everything is satisfied by this thing. So this way we can constructed a bijective homomorphism phi 0. This means if we replace 0 by 1, 1 by I, 2 by minus 1, and 3 by minus I, then these two groups are the is the same, but they are different but into Lucas-Heim. So this means we can simply say that this Z4 is isomorphic to this group. We have to taking J is a cube fourth root of unity, is a cube of a complex multiplication group under the complex number. So this we have to discuss that by the definition. We can define some isomorphism, and that means simply we can say that we have to find a bijective homomorphism from these two groups. Then these two groups look like the same, and then they hold the same properties of all the group. So this means this way can say is these two groups are isomorphic. So now I stop this today lecture here, and we continue next class some other examples of a showing that the isomorphism and some not a isomorphism, and then we have to start some properties of isomorphism. Thank you very much.